All right, I'm going to try something a little bit different with your class today. I tried it with one of the other classes, and the feedback I got on it was that they actually liked it because they were able to follow along, and it felt a little bit less rushed for them. It was about the same amount of information, but felt that I wasn't rushing through it because I was doing all of the work here. The setup's a little bit different as well because I'm doing it from home rather than at school. So today we're going to talk about tangents. These are not the tangents that we talked about in relation to like sine, cosine, and tangent. It's going to be a different kind of tangent. When we talk about tangent in chapter 10, we're talking about tangents and circles. So a tangent by definition is going to be a line that intersects a circle at exactly one point. A line that intersects a circle at exactly one point. All right. I left one part out of the definition here because it doesn't really apply to what we work with, and that is the line and the circle have to be in the same plane. But everyone that we're going to work on is going to do that, so we don't need to write that part. The point, so this exactly one point, this is called the point of tangency. Sorry. Right. That's not a division sign, right? Just renaming without having to rewrite. So exactly one point, it's called the point of tangency. And I'm going to freehand my circles today rather than using a compass to do it, just to show you that you can. If you have a compass and would rather use it, go ahead and use it, but we'll just freehand as much as you can. So what are we talking about here? So if we have a circle, right, a tangent is a line that's intersecting the circle at exactly one point right there. And we might call that point T, and point T is the point of tangency. All right. More than one circle can have the same tangent. So if we had two circles, and a line like that, they both have a point of tangency. This is called a common tangent. You don't have to capitalize tangent. It can look a few different ways as well. I'm drawing it smaller because it doesn't really matter that much. It's not the most important thing. It might also look something like that. Or even something like that. All right, so those would be called common tangents. All right, we're going to look at the first theorem for this section. There's only two. Don't worry, there are only two. It's going to be theorem 1010. And before we actually write out what it is, we're going to take a look at how it looks. So if we have a circle, I'm going to say that's my worst circle so far today, and a tangent drawn to the circle if we were to draw a radius of the circle to the tangent line. So the radius of the circle that goes, sorry about that. There we go. Worst circle, and you couldn't even see it. So we have our circle, the radius, and a tangent line. Think to yourself, what does it look like is true about the radius and the tangent line to the circle, drawn to the point of tangency? And if you guessed that they are perpendicular, you would be correct. So in a circle, a tangent line is perpendicular to the radius drawn to its point of tangency. In a circle, a tangent line is perpendicular to the radius drawn to its point of tangency. All right. Theorem 1011. And if you're counting, this is our last one for the day. Last theorem. We do have one more definition to look at. If we have a circle and we have points of tangency coming from the circle meeting at the exact same point outside of the circle. What is true in this diagram? Well, you might guess, my diagram's not perfect, right? That the only thing that even really makes sense to say here, there's not a lot, well, maybe A, B, and BC are congruent, right? Maybe they're congruent. It's not clear that they are, but it's possible, right? Well, let's take a look. Okay, first note that APC is not 180 degrees. This is not a diameter. AC is not a diameter, right? They are two radii of a circle, AP and PC, which means that AP and PC must be congruent, right? Given that AB and BC are tangents from theorem 1011, we know that these two angles are right angles, right? And if we draw in segment PB, right, PB must be congruent to itself. We now have two triangles, APB and CPB, and those two triangles must be congruent by, well, PB is the hypotenuse of both triangles, and AP and PC are congruent. So by hypotenuse leg, the two triangles are congruent, therefore their corresponding parts are congruent, and AB and CB must be congruent, right? So if two segments from the same exterior point. Tangent to a circle. Then they are congruent. Right? And the last thing we need to look at, I might use this space in the corner here. The last thing we need to look at is kind of a definition, just something we need to know. Circumscribed polygons. Okay, so circumscribed polygons. The first thing that I want you to do, that we have talked about this before, there are two parts of our word that we should see here, right? Circum means around or just round, right? Scribed means to write. So it means to write around, right? So a circumscribed polygon might be something like, oh, forgive me. Pretend that's a circle, and pretend it's a good circle. It's not gonna be that bad. I mean, it's a terrible circle, but if yours is that bad, it's okay, right? We're gonna still get what we are. This is a circumscribed polygon. The polygon, the triangle, is circumscribed about the circle. So it's circumscribed about the circle. Scribed about the circle. We have actually talked about this exact diagram before, right? Because we talked about what this point is, right? It is equidistant to the sides, and it is called the incenter, right? Not important, just a reminder of something we already looked at, right? This can happen with any other figure too, right? You can use a better square than that. And a better circle, right? The square is circumscribed about the circle, right? It still works. Though we wouldn't call the center an incenter probably. Right, let's look at a few examples. So the first would be, are the segments tangent? Okay. So if we have a circle, it has a center of G, H, and I are 2 points on the triangle. H is the point of, well, we're trying to decide if H is the point of tangency, if this line even is tangent, right? So how do we decide if this is tangent? Well, in order for this to be tangent, what has to be true about GH and HI? Well, they would have to be perpendicular, right? do we have a way to determine whether H is a right angle in a triangle? And I hope you say yes, from chapter 8. This is the converse to the Pythagorean theorem. So the question we're asking ourselves is 9 squared plus 40 squared equal to 41 squared. Well, 9 squared is 81. So, and 40 squared, we get 1681. Is that equal to 41 squared? It most certainly is. So yes, segment HI is tangent. All right, how about this one? I made a mistake in my notes. So we have AC and B. We have AC is 4. I didn't do this on the last one. BC is 13. And we got AB is 12. So maybe you just look at that one and you go, well, I know if 13 is the hypotenuse, that's the longest side, and 12 is another side, right? You might already know what this would have to be. And the answer is not 4, right? But if you don't, you do 4 squared plus 12 squared and ask yourself if that's 13 squared. 4 squared plus 12 squared is 160, which is less than 169. This is not a right triangle. It is an obtuse triangle. So you would say no. All right, next ones we're going to find x. And we're going to do something we don't do a lot in geometry. We're going to assume lines that look tangent are tangent. Right? So we're going to assume that lines that look tangent are tangent. R, P, Q. So P and Q are points of tangency. We have W, which is an exterior point. And, well, we know that those two segments must be congruent because they are tangent going to the same exterior point. So 3x minus 6 must equal x plus 10. 2x equals 16, and x is 8. Give you another one. B, A, and C. And I'll let you do that one on your own. Oops. Oh no. All right. All right, so we should get 4x plus 2 is 2x plus 8. Again, it fits the theorem. A is the exterior point. B and C from the directions must be the point of tangency. So the two lines, the two segments must be congruent. Subtract 2x from both sides. Subtract 2 from both sides. And we get x is 3. All right, we have EFG, and we have FE is 8, that's the radius. FG, the tangent, is X. And the hypotenuse is 17. Again, we know that this must be a right angle because FG is tangent to the circle. And let's see, before you try to use the Pythagorean theorem, I wonder if any of you know what the answer is before doing that. So think about it. This is one of our Pythagorean triples that we've looked at a little bit. So if you know what it is, you might just say it is 15. Otherwise, you would do 8 squared plus x squared equals 17 squared. Subtract 8 squared from both sides, take the square root. I don't always do it this way. I actually like it better. That way you can just put into your calculator the square root of 17 squared minus 8 squared, which is really all we care about. We don't care about what the other parts are. And you get x is 15 very quickly that way as well. Just remember you're allowed to laugh at my circles, but I will probably see some of yours at some point. So unless yours are better freehand, probably smarter not to laugh at mine. X, 24 and 10. And again, take a moment to try to do it. Oh, that would have been wrong. This is again a Pythagorean triple. We have 10 squared plus 24 squared equals x squared. We take the square root of both sides, we get x equals the square root of 10 squared plus 24 squared, which is 26. All right. The last two problems we're going to do, find x and the perimeter. Okay, so if we have a triangle, with a circle drawn in, so the triangle is circumscribed about the circle. Q, T, U, P, R, and S. This is 13, 2x, 2x, 9, 4, and that's all we know. All right, so what you hopefully will notice in the diagram is that all of these parts, because the triangle is circumscribed about, well, I'm going to work on this. I promise I'll get better. There's your triangle. You were just sitting there wondering what in the world I was talking about. Pause it, copy it, and then we'll continue. So start after you have it copied. All right, so because the triangle is circumscribed about the circle, that means each of these segments are tangents, right? So PQ is a tangent, QR is a tangent, and PR is a tangent. That means that from R to U and S to R are the same length. They are both 13, right? This must be 4, and PS must be 9. So that means 2x is 9, and x is 4.5. The next is just the perimeter. So we have 4 plus 4 plus 13 plus 13 plus 9 plus 9, and we get perimeter is 52. Oh, this is so bad. Okay, I think I topped my worst one for the day. 5x 13, 5, and not to scale. Actually, it's probably backwards on scale. All right, so first is answer what is x? And hopefully you decided against the scale of the figure that x is 13. This is 13. The length here is 5. The length up here is 13, and the length here is 5. So we have 5 plus 5 plus 5 plus 5, or 4 times 5 for perimeter, plus 4 times 13. That's 20, and 52 is 72. All right. Do not have the homework here right now. You can just find it on Canvas. Yeah, you can find it on Canvas. And if you have any questions, make sure to let me know. Email me and we can get together. For now, given how many people haven't been using the half-hour time that I've allotted, I end up sitting on Zoom for a half hour to talk with one person or two people for like 5 minutes each. If you have a question, please just email me and I will get back to you. Give me like 10 or 15 minutes after you send the email at least at a time for a time to meet. So if you're emailing at 10:15, ask if I can jump on at 10:30, and then make sure you check your email often. Usually I'm available pretty quickly if needed.